Alrighty, hi everyone. I will be going through the mock final exam. I thought this would be a good video in order for you to see how I go about answering each question and like my thought process and how I would just go about answering a final or taking a final exam. So for this, I just have my calculator and I'm taking it on my iPad so I can show you. But yeah, I put a couple of breaks in between here. So I think I do the first like 11 questions and then the next 12 or 13 and then like the rest of them or whatever, whatever that break is. I think there's 3 breaks in here. When I post this video, I will post it so that you can see like questions 1 through 11 take this much of time and stuff. It's in case there's a specific question you need to look for, you don't need to look through an hour-long video. I hope you find this helpful and I hope that if you have any questions that come out from this, please email me what those questions are, or if you think I made a mistake anywhere along the way, please let me know. I am human. That does happen. So with that, we will get started. So this will be a lot of my own thoughts. I will be talking out loud a lot of it at the time too, so I apologize for that. But I'll be annotating this and taking it like I would a regular final exam. Okay, I'm gonna have a fun color though, because that makes everything better. Okay. At laboratory conditions, a 6.5 gram sample of gas has a volume of 5 liters. What is the identity of the gas? Okay, so this I know is going to be STP. I'm looking for the identity of the gas, and that's going to be from molar mass. So I know that I have volume and I have grams. So if I look at PV is equal to nRT, then I know that N is equal to the number of moles. And so I can get molar mass is equal to grams over moles. So if I have N equal to grams over molar mass, then I can do this into here. So then PV is equal to mass times RT over molar mass. So then molar mass is equal to RT times P over V. So then I can plug everything that I know into 6.54. This I need to convert to Kelvin, so this will be 25 plus 273. Okay, so here I know that my liters will cancel out, my ATNs will cancel out, my Collins will Wester out. So I'm left with grams over moles. And I know that my molar mass is going to be in grams per mole. So that looks good. So I can plug this into my calculator. Okay, and I end up with 32.00 grams per mole. And that'll be O2. Okay. Okay, which element is oxidized and what oxidation state does it end up at? So oxidized, I know is going to be more positive. And in terms of oil, and I want to be losing electrons. So oxygen will be 0 and iron will be 0. This becomes -2. This will be +3. So more positive. -2 times 3 -6. So -6 plus x is equal to 0. And then x +6 plus 6 divided by 2 is plus 3, so each iron is plus 3. So this is getting more positive, which is oxidation. And so that'll be E iron plus 3. Okay. What is the delta H of the following reaction? Okay, so I'm given my heat of formations. So I know that I want to use my delta H naught of reaction is equal to the sum of my products minus my sum of reactants. Okay. Looking at this, I don't see O2, and I know that this is going to be 0 because the heat of formation of the element is 0. And then I know that I have my coefficients. So when I do delta H naught, I know that my products have to go first. So that's going to be 6 times heat of liquid. So that'll be negative 241.8 kilojoules per mole plus 4 times carbon dioxide is negative 393.5 kilojoules per mole. And then minus the sum of my reactants, which is just ends up being that C2H5OH. That'll be 2 times negative 277.6 kilojoules per mole. And when I multiply by the coefficients of the 6, 4, and the 2, that's like the molar coefficient. So that's going to cancel out the moles. And so that'll just give me my kilojoules that I'm looking for at the very end once I add that up. So good to plug that into my calculator. I'm going to do it in 2 separate steps. I'm going to do my products and get that, and then add that to my reactants. So I got negative 8 kilojoules minus 2 times negative 277.6 be negative 2. This becomes negative 3024.8 plus 5,552. So I'll do negative 3024.8 plus 5552. I get I think I've put something. So I got 2527.2 kilojoules, and that is not an answer I see. So where did I go wrong? Okay, let's try. Let me look at my products again. So I have 6 times negative 241.8 plus 4 times negative 393.5. Negative 3024.8. Negative 3024. Okay, so that's good. And then I have minus, or I have 2 times negative 277.6. Oh, that's what I did. This is point. Okay, so it becomes 555.2. Okay, so add negative 3024.8 plus 555.2. Okay, there we go. Now I get negative 2469.6 kilojoules, and that's close enough to D. So I'm going to go with D. Okay, moving on. Determine the specific heat capacity of a 15-gram sample alloy of 150.0 grams alloy sample that requires 59.3 kilojoules to raise the temperature from 25 degrees Celsius to 125 degrees Celsius. Okay, so I'm not given a delta heat of fusion, and I'm just trying to find the specific heat. So I'm going to assume that's the only one that I use. And when I see specific heat, I automatically think Q is equal to MC delta T. So I see that my units are given to me in Celsius, so I'm not going to change my temperature. And then I can use grams, and I'll probably have to change it to joules and out of the kilojoules, but we can do it at the very end. So right now I'll say that it requires 59.3 kilojoules for 150.0 gram sample. I don't know my specific heat, which is C, so that's going to be X, and my delta T is final minus initial. So I'm raising it from 25 to 125, so it's going to be 125 minus 25, which ends up just going to be 100. So kilojoules, I know, is 59.3 kilojoules is just going to be times 10 to the 3. So this will be 59.3 times 10 to the 3 joules is going to be equal to 150 grams times X times 100 degrees Celsius. So when I divide 150 times 100, that'll get me to my joules per grams per Celsius, which I'm looking for in my units for in my answer. So I'll do 59.3 times 10 to the 3rd divided by 150 divided by 100. So I get 3.953 joules per gram times Celsius. And that looks like D. Okay, a gas mixture is made up of 0.951 grams of methane and 0.875 grams of F2 gas. What is the mole fraction of methane? Okay, so when I look at mole fraction, I'm looking for number of moles. And I know that my mole fraction is going to be N of something. So in this case, CH4 over my N total. So I need the total moles of both of my samples, and then I just need to look at the moles of methane. So I'll need my molar mass, 0.951 grams. And then this will be 16.05 grams equal to 1 mole. So I get 0.05925. And then I'll do 0.875 grams. 1 mole is equal to 38.0. And that's 0.02304. Okay, so just looking from this, I know that I should have a higher mole fraction for methane, because there's already more moles in it than the fluorine gas. So I'm expecting a number greater than 0.5. So I would pretty much rule out those because they're not close to 50-50. So I'm going to guess it's either going to be 0.68 or 0.72. So I'll add these two up and I get a total of 0.8228. And then I can take my N fraction will be 0.05925 divided by 0.08228 is equal to 0.72. Awesome. So I'm expecting a number greater than 5, and I got that. So I'm pretty happy with that one. We'll call that C. And keep going. Okay. So determine the delta H of the reaction. So I'm looking at a whole thing and I'm giving 2 half reactions. So this immediately tells me that this is a Hess's law type of problem. So I'm going to look to how I can manipulate the given equations below with their delta H's so that I end up back at the original chemical equation that they gave me in the question. So I'm going to first look for my NOCl2 or my NOCl. I see that down here. So that's in my given equation is on the opposite side. So I definitely know that I need to flip this equation, which means I need to negate my delta H. And then there's a 2 in the reaction I'm looking for, and there's no 2 here. So I know I'm going to need to multiply by this 2. So if I flip that and multiply by 2, then 38.6 times 2. I know this will be is going to be 77.2 kilojoules. Okay, so then if I flip that, I don't see the NO gas anywhere. So this now ends up as 2NOCl gas going to 2NO and Cl2. So Cl2 is on the right side, but I need to get rid of this NO. And now here and here, those are on the same side. So I know I need to flip this one too. And then these are given in halves, and I have a whole number here. So I'm also going to multiply this one by 2. So now my delta H becomes at least a negative, and then 90.3 times 2 will be negative 180.6. Okay, and then I end up with 2NO gas going to N2 gas and O2 gas. So if I add those two up, my NOs are going to cancel out, and then I'm left with 2NOCl, N2, O2, and Cl2. And that matches the equation I'm looking for. So I know I can just add these two values here. So I have negative 180.6 plus 77.2, and I get negative 103.4 kilojoules, and that looks like B. Awesome. Okay. For a particular process, Q is equal to negative 25 kilojoules and W is equal to 30 kilojoules. So which of the following statements is true? Okay. So for these type of questions, I like to prove to myself or write out what I expect or what I know from these equations or from these variables as first. And then I look at each of the answer choices and then say either they're false or they're true and why that would be the case. So first looking at Q, when Q is negative, I know that I know that heat is flowing from the system to surroundings. And when I know that when W is equal to 30 kilojoules, I know that work is being done on the system by the surroundings. Okay, so that's what I know just based off of the question without even looking at the answer choices. So for A, heat flows from the system to the surroundings. What did I just say? Heat is flowing from the system to the surroundings. Okay, so I think this is true. So A might be our choice here. For B, the amount of energy of the universe increases. Okay, I know this is false. We can't change the energy in the universe. The energy in the universe will stay the same. So that will never decrease nor increase. So this one's going to be false. Delta U is equal to negative 5 kilojoules. Okay, so delta U is going to be equal to Q plus W. So if I were to add that, it would be negative 25 plus 30, and that would be a positive 5 kilojoules. Okay, so that's going to be false. The system does work on the surroundings. Okay, what did I say? Work is being done on the system by the surroundings. The system does work on this. No, that would be opposite. So that would be a negative. That would be false because that would be a negative W if that's what we were looking at. Okay, and then the process is endothermic. If heat is flowing from the system to the surroundings, then this would be an exothermic reaction. So this would be false. This is exothermic. So this is also incorrect. So A seems to be our answer choice here. Alrighty. Question number 8. How many grams of zinc metal are required to produce 4 liters of hydrogen gas at STP according to the chemical equation shown below? Okay, so I'm looking at zinc here. I'm going to make sure that my equation is balanced. So I have zinc, H, 2 H's, 2 H's, 2 chlorines, 2 chlorines. Okay, so this is a balanced equation. So my zinc to hydrogen is 1:1. I know that at STP, 1 mole of gas takes up 22.4 liters. So I think I can use that somehow to my advantage here. Okay, so how many grams of zinc metal are required to produce 4 liters hydrogen gas. Okay, so I know I have 4 liters. So I'm at STP. Okay, so 4 liters. So if I'm gonna have less than 22.4 liters. So I'll have 1 mole is equal to 22.4 liters. And this is of H2. So then I can use my molar ratio. And I'll say that 1 mole of H2 is equal to 1 mole of zinc. And if I'm in moles of zinc, then I can use the molar mass of zinc. Should have had that pulled up. I should have known I needed that. Zinc is going to be 65.38. Alrighty, so I have 4 times 65.38 going across and then divide by 22.4. Okay, so I'm left with 11.675 grams. Is that an answer choice? Okay, so I see 11.5 grams or 11.7. Yeah, if we round this, would be 11.7 grams of zinc. And I feel good about that. So I'm going to say B for this one. Okay, what is the chemical formula of iron 2 phosphate? Okay, so I know that iron is Fe, and this Roman numeral 2 means it's going to have a +2. And then phosphate is one of my polyatomic ions, and that's PO4 3-. So those are opposite charges. So we can take this one, bring it down here, and this one and bring it down here. So it'd be Fe3 PO4 2. And that's D. Awesome. Okay. Calculate the mass percent composition of lithium in Li3PO4. Okay, so I need the molar mass of lithium and then the molar mass of that whole thing. So in the molar mass, I'll have 3 lithiums, which is 6.94 plus phosphorus, which is 30.974, and then 4 oxygens at 16. So my total molar mass is 88.794 grams per mole. And then my lithium is going to be 3 times 6.94 because I have 3 lithium molecules in my whole compound. So 3 times 6.94, this will be 20.82 grams per mole. So if I divide 20.82 divided by 88.794, then I get 0.2344. That would be times 100, take it to percent. And that's 23. Okay, I don't see that. So let's check my math again. Let's check our molar mass again, because it's 7 times 3 would be 21. So I think my molar mass of lithium is fine in terms of how much that is. So maybe I just plug something into my calculator wrong for the overall molar mass. I only have 1 phosphorus, okay, and then 4 times 16.00. Oh, yeah, I totally missed something. Okay, so this is 115.794 grams per mole. Okay, so now I can take 20 and divide it by 115. Okay, so then this would not be 233. Still need to multiply by 100, so I'll take 20.82 divided by this answer. Okay, and this is about 19. Okay, so this is 0.1798 times 100 would be 17.9. 8. Okay, and that's D. Now I got an answer. Okay, I feel good about that one now. Awesome. Moving on, we have the mixing of which pair of reactions will result in a precipitation reaction. Okay, so let me go find the solubility chart from exam 3, I believe it was, and then to this one. Again, probably should have had this one pulled up, but we live and we learn. Okay, exams. So basically when I'm looking for precipitation, I guess the reason I needed to know I needed that is I'm looking for my solubility. My solubility chart, so I would immediately go look for that one. Okay, so I also know that these are going to form products. So I'm going to write out my products. So these would switch maybe magnesium, CO3 and NaNO3. NaNO3 and CuSO4. I'm not going to worry too much. I just want to switch my partners. So it would be NH4Cl4 and lithium-S. And then this would be, that really is not going to change. It's going to be NH4I and NH4Cl. Okay, so I know that my NH4 will always be soluble. So I know that this is soluble and this is soluble. So that won't work. This is soluble, so that won't work. I guess that won't work. I have to look at lithium. Lithium is usually soluble and there's no exceptions. Okay, so this won't work. Let's see out of the chart. NaNO4, that, or NaNO3, that will always be soluble. So this one doesn't work. And then copper sulfate. Let's see. Sulfates are usually soluble, except for silver, mercury, lead, calcium, strontium, and barium. Okay, that's none of those. This one will be soluble. And then NO3 will be soluble and magnesium carbonate. So CO3, 2- is usually insoluble except for group 1A. So not magnesium and NH4+. Okay, so this one will be solid. So that forms a precipitate. So that's going to be A here. Awesome. So it's not none of the above because we do know that magnesium carbonate will form a solid. Awesome. Okay, so that is the first 11 questions. I'll put a little pause here for the question 12 through 23 next. Give a brief moment. I'll take a sip of water. Keep going. Alrighty, moving on. Keep on checking on. Okay, so next I want to calculate the energy of violet light emitted by a hydrogen atom with a wavelength of 410.1 nanometers. Okay, so when I think of this, when I see wavelength, I immediately think of my lambda V is equal to C. And I'm looking for energy, so it would automatically make me think of my energy is equal to H frequency. I know that'll also be on my formula sheet, so I can look there too, but I'm definitely looking for something with wavelength, which is lambda, and energy. So just looking at this, I know that I don't have frequency, but I can see that I can solve for frequency in my speed of light equation. So I'm going to say lambda frequency is equal to the speed of light. So frequency would be equal to the speed of light divided by lambda. And I can plug that into my energy formula. So I know that E, or energy, is equal to HC over lambda. Okay, and then I can solve for energy. I think I have everything else. H is going to be a constant, C is a constant. Those are both on my formula sheet. And I have wavelength. Excuse me. Okay, so when I have H, that's going to be 6.626 times 10 to the negative 34 joules times seconds times 3.00 times 10 to the negative 8. Oh, not negative 8 times 10 to the over. .00 times 10 to the 8 meters over seconds. And then divided by, okay, nanometers, I see I have meters in my speed of light. So nanometers can be times 10 to the negative 9. And I can prove that by doing 410.1 nanometers, and then 1 nanometer is equal to 1 times 10 to the negative 9 meters. So that's 410 times 10 to the negative 9. This would be 410.1 times 10 to the negative 9 meters. And then my seconds cancel out and my meters cancel out. So I'm just left with my joules. It's what I see in my reaction or my answer choices. Okay, so I'll do. Okay, and then divide by 410. I get 4.85 times 10 to the negative 19 joules. And I see that at A. So I'm happy with that one. I think that is the correct answer. So I'm happy with that. All right. Question 13. How much energy is required to heat 87.1 grams of acetone with a molar mass of 58.08 from a solid at minus 154 degrees Celsius to a liquid at 42 degrees Celsius? Okay, so what immediately points out to me is I'm going from solid to liquid. So I definitely have a phase change, which is why I need the delta H of fusion. And then I see that my liquid or my melting point is going to be at negative 95. So I'm going to go through that. So if I were to draw one of the heating curves, I would be going from here to here. So I go up to the melting point through the phase change, then up a little bit after in the liquid range. So I should have three components here. I know that I'll need Q is equal to MC delta T, and I'll also need Q is equal to the delta H of fusion times N. Okay, so other thing that points out to me is moles here in my delta heat of fusion. So I definitely need to change my mass component to moles as well. So I'm going to do that first. I'll do 87.1 grams of acetone is 58.08 grams per 1 mole. So I should get a little bit more than 1. So like 1.5 moles we can use, that would be good. Okay, so then I'm going to have Q is equal to MC delta T plus delta H of fusion times M plus MC delta T. And this will be my solid, and this will be my liquid component. Alrighty, so let's get after it. Okay, Q is equal to the heat of solid is my C solid, 1.65 times 10 to 1.65 joules times grams times Celsius times final minus celestial. So I'll have to, my final is going to be the phase change, which is negative 95. So I'll have negative 95 degrees Celsius minus negative 154 degrees Celsius. And then plus delta heat of fusion, which is 7.27 kilojoules per mole times 1.5 moles. And then plus the MC delta T again. So I'm not going to That'll be 8.71. This time it'll be the liquid, which is 2.16. And then this is going to be minus 42 degrees Celsius minus -95. That's what that one's going to be. Okay, so I'm going to do these all separately first. So I have 87.1 times 1.65 times -95 minus -154. So this is Q is equal to 8479.2 joules plus 7.27 times 1.5, 10.905. This is going to be in kilojoules. And then 8.71. Oops. 87.1 times 2.16 times -42 minus -95. Okay, and that's plus 9971.2 joules. Okay, so now I have joules and kilojoules here. So let's do my joules together. So I'll do 8479.2 gets me to Q is equal to 18450.4 joules plus 10.905 kilojoules. And kilojoules is just like saying times 10 to the -3. So Q will be equal, or 10 to the +3. So 18450.4 joules plus 10.905 times 10 to the -10 to the third joules will equal plus 10.905 times 10 to, okay, 29355.4 joules. And then if I want to get to kilojoules, 1 joule is 1 times 10 to the -3 joules times 10 to the -3. So this will be Q is equal to 29.4 kilojoules. Awesome. Answer choice B. Okay, that's a lot of work. I might break that up a little bit more if I had to do that again, but I got a right answer, or I got an answer choice, so I'm going to be happy with it. Okay, how many milliliters of 0.111 molar hydrochloric acid solution are needed to neutralize 50 mils of the sodium hydroxide solution? Okay, so I recognize this as a strong acid and this as a strong base. So I'm just going to write out what the neutralization reaction would be. So it would be HClO4 plus NaOH. This will form NaClO4 and H2O. And that is balanced, so I don't need to do anything with the coefficients. So that's just good to use a 1-to-1 ratio, which means I can just use the M1 or MABA kind of equation. So I know that I need 0.111 molar, and then I don't know what volume I have of that, but I know that I have 50.0 mils and 0.0789 molar. So just looking at this, since it's a 1-to-1 ratio, my concentration of my acid is going to be higher than my concentration of base. So I should need less acid to neutralize the base because it's a little bit higher in concentration. So it'll take less to get to that, to neutralize all 50 mils. So I'm expecting an answer of choice less than 50 mils. So I have 50 times 0.0789 and then divide by 0.111. Okay, so X is equal to 35.5 milliliters. Awesome. B is here. Sweet. Okay. Next, we have give the ground state electron configuration for strontium. Okay, back to my periodic table. So electron configuration for me is going to think SPDF if I'm not looking at any of my answer choices. And then I'm looking at my answer choices too, because I'm going to use that to my advantage. So I know I'm probably going to look at krypton first. So krypton is element 36, and then strontium is element 38. So if I were to write this out myself, I would say strontium is going to be krypton, and then it's 2 in, so that'll be sp2, and I get there. So I think that looks good to me. I think that's all I need. Is there anything else? No, I don't get to the D subshell. I don't go through the P. Nope, I think I'm good with that. I just need 2 extra electrons to get from 36 to 38. Yeah, that looks good. I'm going to go with D. Alrighty. Question 16. So a basketball is inflated to a pressure of 1.8 ATM at 23 in a 23°C garage. What is the pressure of the basketball outside when the temperature is -2? Okay, so I would be thinking about my gas laws. So I think like PV is equal to nRT, and I know my combined gas law is PV P1 V1 over T1 is equal to P2 V2 over T2. I'm just talking about pressure and temperature here, so I think I'm just going to be looking at P1 over T1 is equal to P2 over T2. And I have 3 out of the 4 components. So I know I need to change my degrees Celsius into Kelvin. So that's going to be my first thing. So I'll say 23 plus 273 will be equal to 296. And then -2 plus 273, I get 271. Okay. So it's inflated at a pressure of 1.8 ATM. So this will be P1 in A23s. This will be temperature 2, or not temperature 1. And then this -2 is temperature 2. Okay, so I'm looking for pressure 2. So I have 1.80 ATM over 23, I said was 296 Kelvin, which is equal to X over 271 Kelvin. Okay. Okay, X is equal to 1.65. See, awesome. Okay. How many electrons are in the ion nickel 2+? Okay, I'm going to go back to my periodic table. So nickel is element 28. So a neutral nickel would be 28 protons and 28 electrons, but it's 2+. So that means I'm losing 2 electrons since electrons are negative. So 28 minus 2 would be 26. So 26 electrons. Alrighty. How many protons, neutrons, and electrons in an atom are represented by, this is not a question mark, this is actually 139, this is 57, and this is LA plus. Okay. So this I know is my total mass. And this is my number of protons. So I know I have 57 protons, so that doesn't eliminate anything yet. My neutrons will be made up by the number of protons plus the number of neutrons equal to the total mass. So my neutrons are going to be 57 plus X is equal to 139. That's going to be X is equal to 82. And then I have a plus charge, which I remember from the last question that a plus means I lost electrons. So 80, so I have 57 minus 1 will be 56. Okay, so I'm looking for 57 protons. It's not going to be these two. I have 82 neutrons. And then I have 56, I wrote 52, 56 electrons. This one here, E. Awesome. Okay, how many electrons can be contained in all of the orbitals with n is equal to 4? Okay, so I know my orbitals. If I think about my quantum numbers, n is my energy level, L is my subshell, and then my orbitals with n is equal to 4. So I think this means I know that I can have L is equal to 0, 1, 2, 3, and that's going to be S, P, D, and F. So I know that my s orbital, is this the subshell? I don't remember what this is. It might not be subshell, question mark. So I think this is 0, 1, 2, 3 for my orbitals, and that's going to pertain to my orbital. Okay, no. This is my orbital. I got it now. This is my orbital because M is the subshell. Okay. So N can be equal to 0, 1, 2, or 3. So in my S, I have 2. In my P, I have 3. In my D, I have 5. And my F, I have 7 orbitals. I'm still confused on L and M. So I'm just going to give myself a question mark here. But I think I know that L is going to be related to 1, 2, 3, or 4 because L can only be n minus 1. And then the 0, 1, 2, and 3 corresponds to my s orbital. And so I know that I can have not 1, not 2, but I can have, this can be 1, 3, 5, or 7. And then each of those orbitals within the subshell. So maybe I flip these, whatever. But the s can only hold 2 electrons because there's only 1 orbital. So I know I can have 2 plus 6 plus 10 plus 14. So 2 plus 6 plus 10 plus 14 is going to be 32 electrons. Okay, I think that is correct. How many electrons could be contained in all the orbitals with n is equal to 4? Yeah, I think that's correct because in n is equal to 4, you can have s, p, d, or f orbitals. And each one of those the s orbital can hold 2. Yeah, I feel good about that one. I think it's going to be A. I might have switched around my L and M, but I think without looking at like what each of the quantum numbers means, I think that's still the answer choice you're looking for. Okay, I'm going to keep going. Maybe I'll put a star by this one, and we'll come back and look at that later. All right, so for question 2, I have gallium has an atomic mass of 69.723 AMU, and then we have a percent abundance, and what's the mass of the other isotope? Okay. So this one immediately jumps out as a percent abundance question to me because of the word abundant. So I know that my atomic mass will be equal to the mass 1 times percent plus the mass 2 times percent in simpler forms. Okay, so I think, and I know that my percents have to be equal to 100. So 100 minus 60.110 is equal to 39.89%. Okay, so my other one is going to be equal to 39.89% abundant. Okay, so I'll do 69.723. My mass 1 is 60.926, and my percent of this is 60, but I need to change that to a decimal, so this would be 0.60110. My mass of 2, I don't know, so that's X, and then percent abundant is 0.3989. Okay. Yeah, that looks good. So I'll do 68.926 times 0.600. 69.723 is equal to 41.43 plus 0.3989 times X. Okay, so then 69. It's 28.293 equal to 3989 X. So X would equal to 70.93. Somewhere around there. 70.9. I need to do more decimal points. 70.928. Here we go. C. C. Happy with C. Okay. We will move on to question 21. I think another break is coming in soon. Okay, so we want to draw the Lewis dot structure for NO3 minus, I believe it's supposed to be. Yeah, NO3 minus. And then predict the molecular geometry. What is the approximate 0, 0? Oxygen, nitrogen, oxygen bond angle. Okay. So Lewis structure, I don't need to count my valence electrons. So nitrogen will be equal to 5 valence electrons, and I have oxygen is equal to 6 times 3, which is 18. So 18 plus 5 is 23. And then I have an extra electron because the NO3 has a minus charge. So I'll have +1. So I have 24 total electrons. Okay. Least electronegative goes in the middle. So oxygen and then oxygen, nitrogen, and then 3 bonds. So I have 24 minus 6 is 18, I believe. 18 electrons. Okay. Then I'll fill the oxygens first. Be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so that was 18. That was 0. Okay. But my nitrogen does not have a full octet, even though my oxygens do. And if I were to solve the formal charge of this, my formal charge of oxygen here would be supposed to have 6. It has 1 bond and 6 electrons. So my formal charge of oxygen is -1. And then nitrogen, you're supposed to have 5, and it only has 3. So then this would be +2. Okay, so having a -1, -1, -1, and +2 is not good. So we're going to take one of these lone pairs down here and we'll make it a double bond. Yeah, that looks good. So now that has all of them have a complete octet. If we were to solve this formal charge, this would be 6 minus 2 bonds, 4 electrons. 6 minus 6 is 0. This formal charge would be 6 minus 1 plus 6. So that would be -1, which would also be -1 over here. And this formal charge would be supposed to be 5, is actually 4 plus 0 because there's no lone pairs. And so that's a +1. And so we have 0, -1, +1, -1. And that comes out to equal -1, which is what we want all of our formal charges to come out to. So that's our best Lewis dot structure for NO3 minus. Okay. So if we're looking at this, this is now a trigonal planar molecule. There's no lone pairs, so that's going to be 120 degrees. That's neat. Okay, awesome. For question 22, which of the following is a polar molecule? Okay, CCl4, I know this one. That one's going to be nonpolar. BF3, I know is an exception. So that's also going to be nonpolar. TCl5, phosphorus. Phosphorus has 5 valence electrons, so 5 plus 3 times 7. Fluorine is 26. Phosphorus can expand as octets, so it's P and then 5. This is 5 times 7, excuse me. I'm like, that's not going to be enough electrons. 5 plus 5 times 7. 3, 5 plus 5 times 7 is going to be 40. Okay, yeah, that makes more sense. So then I used 10, so that's going to be 30. And then 6 go to each. Okay, 5, that's going to be nonpolar. These will all have lone pairs. Okay, CO2. CO2 I know is nonpolar. So it must be TEF. I could prove that to myself, but TE, where's TE? That's a 6. TEF4, yeah. That kind of reminds me of like, whatever. Okay, this would be 6. I guess I'll prove it. 6 plus 7 times 4. That's 34. So I have TE and 1, 2, 3, 4, 5. 5F minus 8. I guess this could be 26. Then if I did 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 24. So I have 2 left over. Yeah. Lone pairs on the central atom is going to make it polar. Yeah, definitely polar. This one is polar. Awesome. Okay. Place the following in order from smallest on the left to largest on the right, ionic radii. Okay, so I know that the more positive it is, the smaller the atom. So if I'm looking at Y, this SE, where is SE? Okay, SE is number 34. So SE should have 34 protons and 36 electrons. SR2 plus. That's going to be 38 protons and 36 electrons. Y is 39 protons and 36 electrons. And then Br minus is 35 protons and 36 electrons. Okay, so they all are the same as krypton. They all look like krypton. But the more anionic it gets, the bigger it is. So this one has the biggest, this is -2, yeah. So strontium, no, selenium should be the biggest because that has the highest anionic charged. And then yttrium should be the smallest because the cation is going to be, or the more cationic, it means the more smaller the radii we're going to get. So if I put Y and then SR and then BR and then SE, that looks like D. Okay, I'm happy with D. Okay, awesome. So that brings us to our next little break. I'll put this up for a second and then we'll keep going. We're over halfway, so we're kind of almost done with the exam. Alrighty. Next is question 24. I think it was on the last page. So when I made the break, it happened, but here we are. So when a carbon atom has an sp3 hybridization, sp3 hybridization. It has 2 pi bonds and 2 sigma bonds. Okay, so what would that look like? If I just had this, it'd be 2 pi bonds, 2 sigma bonds. That would be pi, sigma. No, that's 2 electron domains. So that would be sp. Okay. 1 pi bond and 3 sigma bonds. So if we had 1 pi bond, that could be like that guy, and then 3 sigma bonds. So that's a pi, a sigma, a sigma, a sigma. That's 3 electron domains, which is an sp2. 3 pi bonds and 1 sigma bond. Okay, so that would be like 1, 2. How does that even happen? I don't think you can even have that. I don't think that exists. How does, no, you can't, that can't happen. I don't think that can happen. We're gonna get rid of C. I don't think that can happen. 4 pi bonds, you have to have a sigma bond if you have a pi bond. So that also can't happen. Or 4 sigma bonds. So 4 sigma bonds would be sigma, 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 sigma. That's 4 electron domains, which is an sp3. Okay, I like E. That was a good question. That made me think. Okay. So this is looking a little funky here, but it is 82.74 divided by 0.181 plus 14.25. Okay. So this one is perform the calculation, report your answer to the correct number of significant digits. So I have 4 on my numerator and then 3 on my denominator. So when I do PEMDAS, I'm going to do my division first. And since 1.181 has 3 sig figs, I'm going to solve it to 3 sig figs. So that should be 82.74 divided by 0.181. That is 457. 3 sig fig, that's it, plus 114.25. And then I'm going to add 114.25. But it's going to go to the least number of decimal points here, which is going to be what I just did from the division. So should only be 571, no extra decimal points. I don't need a decimal point technically because the 1 makes it significant, but if it was a 0, then I would need a decimal point. So I like A here. A should be my answer. Okay. For the hydrogen atom, which transition between energy levels results in the emission of a proton with the longest wavelength? Okay, so I know longest wavelength. I know my wavelength and energy are inversely related. So if I have a high energy, my wavelength is short. So that's like one of my gamma rays. So if I have a long wavelength, I need, then my energy is going to be low. So if my energy is low, I want a small transition. So I can either go from n is equal to 1. Okay, we're just going to draw it over here. We'll have 1, 2, 3, 4, 5, 6. Okay, so I can have n is equal to 1 to n is equal to 6. So where's in the emission of a photon? Emission of a photon. Okay, that's the other key part. Emission of a photon means I have to go from a high energy level to a lower energy level. Okay, so even before I do this, I just want to make sure they go from high to low. So this is low to high. So this cancels out. This is high to low. This is high to low. This is low to high. Okay. So I either have 6 to 1 or 6 to 5. So if I go from 6 to 1, that's a big change in energy. So a big energy means the short wavelength. Okay, so it's not going to be that one. So I think it's going to be 6 to 5 because that would be a short change in energy, and a small amount of energy would be a long wavelength. Yeah, I like that. C is going to be my answer choice here. Okay. 27. Which of the following atoms has the largest first ionization energy potential? Has the largest first ionization. Okay, so I want to remove an electron with this one. And I know if I'm looking at my periodic table, my ionization energy is going to increase as I go across, and it's going to decrease as I go down. Okay, so I have periodic table, I have aluminum, kind of like over here. Xenon is a noble gas. That one's probably going to be it. Zinc is in the transition element, so that's over here. And then neon is up here. Okay, so it's definitely going to be one of my noble gases because noble gases are already at a full octet and they don't want to give up anything. But neon is smaller than xenon. So I'm decreasing my electron energy, first ionization energy as I go down. So neon will have a harder time since it's smaller. So D is going to be my answer choice here. Alrighty, happy with those. Okay. Question number 28. What is the stoichiometric coefficient in the nitrogen gas product when the following equation is correctly balanced? Okay. So I'm going to start with my leftmost atoms. That's going to be carbon. So I have one carbon on the left and one or two carbons on the left, one on the right. So I'm going to put 2 here. And then my nitrogens are 2 here and 2 here, and only, so that's 4 nitrogens and 2. So I'm going to put 2 here. Okay, so let's look at how many oxygens I have. So I have 4 oxygens, 5 oxygens. Oh, that's going to be nuggets. Okay. I guess I should balance. Because this is going to be odd, so this needs to be an even number in order to make it even. So let's just put a 2. Oh, wait. Oh, no, because I have 4 from there. Okay, we put a 2 there, then that makes it 4 oxygens. No, that makes it 6 oxygens, and you can't really do anything with 6 and 4. Okay, so let's put a 4, because I know it has to be even. So we'll erase this. So we have 4 oxygens on our right. So we have 4, and then we know we need 2 is not going to work, so we'll put a 4 here as well. So we have 4 oxygens. This will be 2. Okay, so then we have 4 carbons, 4 carbons. That looks good. This makes it 4 nitrogens plus 2 nitrogens. Hold on, wait, let's go to look at our oxygens first. So now we have, this is 8 total electron, or 8 total oxygens here, 8 oxygens, and this is 4 oxygens. So that's a total of 12 oxygens. And so I can put a 3 here. Okay. That looks good. And then am I getting all crazy over here? And then nitrogen is 4. Nitrogen is 3. Oh, because this is not a 2 anymore. This is a 4. Okay. Then I have 8 nitrogens and then 6 nitrogens. So this goes to 14 nitrogens. This needs to be a 7. Okay, let's check all of them again. So I have 8 carbons. I have 4 times 32. Oh no, am I all screwed up here? Am I all screwed up? 32 hydrogens. 16 nitrogens. No, because that just screwed up all of my 16 nitrogens. Okay, wait, let's look at this. And then 12 oxygens. So then 7. Sorry, this needs to be an 8. This needs to be an 8. I have 4 carbons, which means I have 8 oxygens, and then I have 32 on this. So I do 32 divided by 2 is 16. 16 hydrogens. So that would be 32 hydrogens, and then 16 plus, no, because then it makes it 16. I'm all sorts of screwed up. Okay, I'm gonna pause this recording real quick. Okay, I just took a moment again, and I'm just gonna start over. At this point in the exam, if I were a student taking it, I would have just circled it and come back to it. Because I'm now just spending more time than I would like to on it. But for the sake of the video, I'll keep it, and you can see me downward spiral in terms of trying to balance an equation. And you can either laugh at me, or consider me human. Okay. I think I need to be a little bit more organized with this. Okay, so carbon 2, no carbon. This needs to be a 2. Okay. Alrighty. I have 2 carbons. Carbons are okay. So I have carbon is 4. Carbon is 4. Hydrogen's 8. I only have 2 here. Okay, so this needs to be a 4. So hydrogens are going to be 8, and now hydrogens are also 8. Okay, so then how many oxygens do I have now? So I have 4 oxygens, 4 oxygens. I have 8 total oxygens. Okay, so oxygen is 8. So I have 2. So this needs to be 2. And then now that's 8. And then I have 4, 6. Okay, so this needs to be 3. Okay. Did I have that earlier and I just thought I was crazy? Oops. 4, 8, 8, 6, 6. Okay. Okay, I think that works. I think I got it. I think I just need to step away for a second. In any case, what is the stoichiometric coefficient of the nitrogen gas product when the following equation is correctly balanced? Okay, so I'm looking at this one. Correctly balanced is 3, so it's going to be 3, or it's going to be D3. I don't know what just happened. I'm going to watch this later, and I'll be like, Allison, it was right there. But you know what? Look at that, still making mistakes. Anyways, moving on. Question 29. What is the net ionic equation for the chemical reaction written below? Okay, so when I look at the chemical equation, again, excuse me. I know that for the net ionic equation, I can't break up the solids, gases, and liquids. So I must see this guy, and this guy in my net ionic equation. So I immediately can get rid of A because that does not have all of the components. This does not have all of the components either, so that can't be it. H2O, this is a liquid now. This is saying this is solid gas. Okay. They just changed the signs on that one, so I don't think that one's it. This looks good to me. The D looks good. Okay, and then did they just rewrite? This is the same equation. This is what we're given. Okay, so I know it's either going to be D or E. So I can do H2SO4 is going to split up into H2 and H2. H2SO4 is going to split up into 2H plus and SO4 2 minus. And then this will go to calcium 2 plus and SO4 2 minus. So SO4 2 minus is going to cancel out. That's not going to be in our overall equation. So yeah, I think it's just D. I like D. Because then it has all of our solids, gases, and liquids in there, and it shows the hydrogen ion and the calcium ion are actually like breaking apart or whatever, and dissolving. Okay, I like that. Yep, SO4 is just a spectator ion. I think that looks good there. Okay, nickel 2 sulfate. 154 used for nickel plating can be prepared by treatment of nickel 2 carbonate in sulfuric acid, given that below. Okay. When 14.5 grams of nickel carbonate is reacted with excess acid, The yield is 78.9%. How many grams of nickel sulfate is produced? That's a great question. Okay. So I think I first want to make sure that this is balanced. So here we go again. Nickel, nickel, carbon, carbon, oxygen has 7, 5, 6, 7. Okay, hydrogen, hydrogen. Okay, it's balanced as is. Okay. So nickel is carbonate is reacted with excess acid. So this is our limiting reagent. And they're saying the yield is 78.9%. So how many grams of nickel sulfate is produced? Okay, so I'm looking for how many grams this is produced. So I want to find my theoretical yield of what I expect to get if I had 100% yield. So I have 14.5 grams of NiCO3. And so this is going to be in moles, 150, no, nickel carbonate is 118.70 grams per 1 mole. So this would be 14.5 divided by 118.70. This is 0.112 moles. And then 0.112 moles of nickel carbonate. 1 mole of nickel carbonate is equal to 1 mole of nickel sulfate, and then 1 mole of nickel sulfate is equal to 154.75 grams. So then 0.112 times 154.75 is equal to 18.9 grams. Okay, so then my percent yield equation is actual over theoretical. So I have 0.789 is equal to X over 18.9 grams. Okay, so this times 0.789. So X is equal to 14.9-ish grams. And that's B. Awesome. And I expect to see a little bit less grams produced than what my theoretical is because our percent yield is not 100%. So I'm pretty confident with this answer that it's going to be 14.9. If I did 14.9 divided by 18.9, yeah, that's 78.8%, which is pretty much 79%. Pretty close, probably some rounding in there. So yeah, awesome. I'm happy with that. Okay, moving on. We're almost done. We have like 10 questions left. So a compound containing only carbon, hydrogen, and oxygen is subjected to elemental analysis. Upon complete combustion, a gram sample of compound produced that many of gram of oxygen, of hydrogen. What is the empirical formula of the compound? Okay. So this is going to be combustion analysis. It's CH3 and O and or CH and O, and so that I know automatically know this is going to be a lot of math. So if I was during the exam and I was getting tired, I might come back to this a little bit later. For the sake of this, I'll just keep going as it is. But I first know that I have grams of carbon dioxide and grams of water. I usually draw a little like fake reaction, or I guess incomplete reaction, because I don't know what my numbers are yet. But I know that a combustion analysis will always include the element you're combusting, some oxygen, producing CO2 and H2O. So I just write that so I know what's going on. So I know I'm going to need to find the grams of carbon dioxide. I need to change those into moles. The same thing for the water. So 1 mole of CO2 is equal to 44.01 grams of CO2, and then 1 mole of CO2 has 1 mole of carbon. So I know that I'm going to need both the moles of carbon and the grams of carbon. So I am going to convert all the way to the moles of carbon. But when I plug this into my calculator, I'm going to just divide 0.3051 by 44.01 grams. And so I know that I have 0.0069325 moles of carbon. And then I'll multiply this by 12.01, and then I'm going to get 0.08326 grams of carbon as well. So now I have both of those answers that I'm going to do later. So I'm going to do the same thing for the hydrogen. Okay, so same thing. 1, 2, 4 times 2. And then okay, so I have grams of carbon, grams of hydrogen, moles of carbon, moles of hydrogen. So I know that my gram sample, so my grams of carbon and my grams of hydrogen are going to make up that component of the original gram sample. So in order to find my grams of oxygen, I'm going to sum up those grams and then subtract that from the original sample. So I'll have 0.1804 minus. Okay, so that's, I know I have that many grams of oxygen. And then I can, and then I'll convert that grams of oxygen to moles of oxygen. Okay, that's 0.005196 moles of oxygen. Okay. So now looking at this, I have to find which mole is the smallest. So that looks like it's oxygen because that has 0.005, while carbon has 0.007-ish and hydrogen has way more than that. Okay, so I'm going to divide by the smallest number. So it'll be divide by 0.00519. This one will be 0.006. Okay, so this will be 1.0. So it's 1.33, and then this is 2.66. Okay, so the good thing about this is that 0.33 and 0.66 are both like fractions you would see if you divide by 3. So I can multiply all of these values by 3 to get to a whole number, since I can't use 1.33 or 2.66 atoms in carbon or hydrogen. Multiply all this by 3, so I end up with 3, 4, and 8. Awesome. So then I'm looking for, this is carbon, hydrogen, and oxygen. So I should have C4H8O3. C4, there it is, C, awesome. Okay, great with that one. That one does take some time, so that might be something where you answer everything else and then come back to it, depending on how much time you have left when you get to this question. Okay, moving on. I think I give you a couple more questions here at the bottom of this page. We'll take one more break and then finish up the exam. Okay. Metal hydrides react with water to form hydrogen gas. How many grams of hydrogen gas H2 is formed when 5.62 grams of SRH2 reacts with 4.80 grams of H2O? Okay. So this looks like a limiting reactant question. I know that I have 5.63 and then 4.80. So I know things about my reactants and nothing about my products. So I'm definitely screaming limiting reactant. So I'm I like to solve for like how much of the product can be produced. So I'm gonna find that for hydrogen gas for both of them. So I have 5.63 grams of SRH2, 1 mole of SRH2 is 89.62 grams. And then this has a 1 mole to 2 mole of H2. That's 5.63 times 2 divided by 89.62. That's 0.1256 moles of H2. And then this one would be 4.80 grams of H2O. 1 mole of H2O is equal to 18.02 grams. And then this has a 2 mole of H2 is equal to 2 mole of H2. Okay, so it's like basically just a 1-to-1. So I just need to divide 4 by 18. Then I get 0.26637 moles of H2. Okay, so I produce more by using up all of my H2O than if I use up all of my strontium hydroxide. So hydroxide SRH2. So this strontium component is going to be my limiting reagent. So I'm going to take the 0.1256 moles of H2 and convert that to grams. So I'll take 0.1256 times 2.02. And I get about 0.252 grams. And that's pretty close to E. So if I'm looking at my answer choices, I like E the best. And probably just did some rounding there. I could probably go back and fix it, but right now I like, I might put a little star next to that and come back to it later, see if I can get it closer than 2.52, but I'm happy with that one. If I look back at my calculator, okay, so I actually multiply by 2.01 instead of 2.02, so that's about 2.53 now. So okay, happy with that, like E. Alrighty, question 33. We're looking at what is the concentration of sodium ions in a 500 ml solution containing 10 grams of sodium to SO4, and the molar mass is that. Okay. So in order to get concentration, I need that to be in moles over liter. Okay, so let's convert our grams to moles. So we'll do 10.0 grams. We have 142.04 grams in 1 mole. So I know I have this many moles of my whole sample. So I have 0.0704 moles of N2 of, Na2SO4. Okay, so if I'm looking at this in terms of a reaction, if that is going to become aqueous, then Na2SO4, that will split up into 2 sodium ions and 1 SO4 minus ion. So my molar ratio is 1:2. So if I convert this to moles of sodium, I have 1 mole of Na2SO4 to 2 moles of sodium. I'll multiply this by 2. So I know I have 0.1408 moles of sodium ions in 500 mils. So that's going to be 500 So that's 0.5 liters. So I divide this by 0.5. And I get a concentration of 0.282 molar, and that's A. All right, happy with that one. Okay, how many milliliters of 0.5 molar H2SO4 are needed to prepare 1.2 liters of 0.2 molar H2SO4? Okay, so this, looking at me, I have the same compound on both sides. So this just looks like an M1V1 is equal to M2V2 equation or type of question. So I have 0.5 molar times X because I don't know how much I need. And I'm going to get to 1.2 liters. That's diluting, getting smaller in concentration. So I'm not going to need the total amount of 1.2. I should have something less than that. So it should be 1.2 times 0.2 divided by 0.5. Oops, I did that wrong. 1.2 times 0.2 divided by 0.5. So X is equal to 0.480 0.480 liters. And if I want to convert to milliliters, 1 liter is equal to 1,000 milliliters. That's 480 milliliters, which is C. Awesome. Happy with that one. Okay. The atmospheric pressure at the surface of Mars is 5.92 times 10⁻³ atm. The Martian atmosphere is 95.3% carbon dioxide and 2% nitrogen gas by pressure. The small amounts of other gases also part of that. What is the partial pressure of N2 in the atmosphere of Mars? Okay. So when I think of partial pressure, whatever the pressure of, so the pressure P total is 5.92 times 10⁻³ atm. So if I were to get the partial pressure, the pressure of N2 divided by the total pressure would be equal to 0.027 atm, or 0.027%, or 2.7%, which is 0.027. So I think I'm able to just plug in P total. So this would be PN2 divided by 5.92 times 10⁻³ is equal to 0.027. And I get 0.00015984. And then I want to convert this to scientific notation. This is 1, 2, 3, 4. 1.598 times 10⁻⁴ atm. So 1.6, actually 1.6 atm d. Okay, I'm feeling okay about that one. I think that one's correct. Because the partial pressure is just made up of like the percentage and the moles there. So I think the way we found that is good to go. Alrighty. This is going to be questions 36 through 40 next. We have 5 more questions and then we're done with this exam and done with this video. So we'll take a break one more time and then we'll finish it off. Okay. I think we're going to get started, finish it. Okay, question 36. Which of the following statements is true? So again, similar to like that earlier question with the Q and W questions, I like to just prove to myself which ones are false and which ones are true and go through each question. So a volume of individual gas molecules does not matter at high pressures. So at high pressures, okay, so this is this brings me back to the van der Waals equation. So the volume of individual gas molecules does not matter at high pressures. So at high pressures, they're going to be really close together. And so they might have some interactions. So I think volume might matter here. So this is a maybe. I'm going to see if I can prove the other one's wrong before I say it's going to be A. Okay, the average molecular speed of molecules in 2 samples of the same gas, different temperatures are equivalent. So the average molecular speed of molecules in 2 samples of the same gas at different temperatures are equivalent. So I think that's false. And I'm thinking back to exam 4, and I want to look at my other formula sheets. So I'm going to go back to, let's see if I have the average molecular speed from exam 4 real quick. So I'm looking for average molecular speed. So that's like kinetic energy, related to kinetic energy, the average molecular speed of molecules in 2 samples of the same gas at different temperatures are equivalent. No, so that's going to be dependent on temperature. And so at the higher temperature, they're going to be moving faster because they're going to have a higher kinetic energy. So no, this is going to be false. They'll have different speeds. Okay. The average kinetic energy of a sample of helium is equal to the average kinetic energy of a sample of argon at the same temperature. That's true. That's definitely true. At the same temperature, all of them will have all of them will have the same kinetic energy, but they will be at different speeds. So helium's lighter than argon. So helium will be moving faster, but will have the same kinetic energy as argon. So that's true. Okay, so get rid of B, maybe we feel good about C. D, gases exhibit non-ideal behavior at higher temperatures. That's false. They exhibit ideal behaviors at higher temperatures. In order to make something a gas, you heat it up. And so at higher temperatures, it's going to keep on acting like a gas. So I think this is false. For E, the volume term in van der Waals equation accounts for the intermolecular forces in a sample. No, that is going to be the pressure one. So I think this is pressure. So pressure is going to be the one that is related to it. Volume's determined by the number of moles, which is determined by it actually taking up space. So I think volume matters at high pressure. So I'm going to say that one's false because I feel more confident with C. So I'm going to go with C first. I'm going to feel good about that one, I believe, rather than going with one that I have a maybe about. So I'm going to stick with C. I think I like C better. So we're going to go C. Okay. How much energy is given off when 1 gram of iron is reacted with excess oxygen according to the following reaction? Okay. So I'm starting with iron. Okay, sweet. So I just need to basically use this like I would a product since it's an exothermic reaction. So I'm going to think about my molar equivalent because I know that this is for like 1 reaction. So 1 mole of reaction. So I'm going to get iron. So 1 gram of Fe is going to be 1 mole of Fe, which is 35 or 55, excuse me, 0.845 grams. And then 4 moles of iron is equal to 1,652 kilojoules. So 1.00 times 1652 divided by 55.84 divided by 4. So I get 7.396 kilojoules, which looks like B. I'm going to go with B here. I think that makes sense to me. It's not going to produce all of the energy because we don't have 4 moles of iron. We have significantly less. So we have a significantly less amount of of energy being released. Okay, I feel good about that one. What is the formal charge of the oxygen atom in the structure below? Okay, cool. So formal charge, I know my equation is going to be the valence electrons minus the number of bonds plus the electrons or the lone pair electrons I also think of this as the valence electrons minus the lines plus dots. So the oxygen here is oxygen, clearly. So it should expect to have 6 valence electrons since it's in like that row of the periodic table. And then it has 3 lines because it has 3 dots. It has 3 lines because it has 3 bonds, excuse me. And then it has 2 dots from the lone pair. So this will be 6 minus 5. So this is a +1. So our oxygen atom here is +1. Perfect. Okay, two more, everyone. All right, for number 39, which of the following statements is true? So again, similar to like the one we just solved earlier, intermolecular forces hold the atoms within molecules together. Within molecules. I think this is false. I believe that's intra. Intramolecular forces hold the atoms within the molecules together. Inter, as you think about like, international, you're going between nations. So intra would be within your nation. So I think this is false. For B, hydrogen bonds are stronger than covalent bonds. I believe this is false as well. Covalent bonds, pretty strong. Hydrogen bonds is weaker. So this is false. Hydrogen bonds are stronger than like dipole-dipole interactions, but they're not stronger than covalent bonds. Because covalent bonds are a full dipole, while hydrogen bonds are just, other charges, partial charges interacting with each other. Okay. So I think that's false. And then dispersion forces are generally stronger than dipole-dipole. No, dispersion are the lowest. This is also false. Dispersion forces are the lowest energy level, or the lowest form of intermolecular forces. So dipole-dipole are definitely stronger than that. Dispersion happens between nonpolar molecules, while dipole-dipole happen with partially charged. So I think this is none of the above. I don't think any of these are true. Alrighty, last question. When 5.5 grams of barium is added to 100 grams of water in the container open to the atmosphere, the reaction shown below occurs and the temperature of the resulting solution rises from 22 to 61. If the specific heat of the solution is 4.18, calculate the delta H of the reaction with respect to moles of barium. Okay, so here there's a lot going on, but it's looking like I need to do an MC delta T equation because I need to find the heat there or the Q there, and then I can use the number of moles of barium to get to the delta H of the reaction. Okay, so when I look at Q is equal to MC delta T, my mass is going to be of the barium and of the water because that will create my whole solution. And I'm looking for the specific heat of the solution given to me, so I need both components in there. So specific heat. So this will be masses in grams. So this is just Q will be equal to 105.50 grams. Specific heat is 4.18 joules times grams times Celsius. And then I can do final minus initial. So that'll be 61.16 minus 22.00 degrees Celsius. I can say in Celsius because my specific heat is in Celsius. Okay, so I can have my Q is equal to 105.5 times 4.18, 61.16 minus 22. Okay, so I get Q is equal to 17269.1684 joules. And if I want to convert that to kilojoules, this will be 1 joule 1 times 10 to the negative 3 kilojoules. So 17.269 kilojoules. So then I know that this is Q of the solution. which is equal to negative Q of the system, or Q of the reaction. So if Q of the solution is 17, then Q of reaction is equal to negative 17.269 kilojoules. Okay, and then I need to convert my 5 grams of barium to moles. So 5.50 grams of barium. 1 mole of barium is equal to 137.33 grams. So I have 0.04005 moles of barium. So I'll take this divided by 0.04005 moles, and I get negative 17.269 divided by 0.04005. And that is negative 431 kilojoules per mole of barium. And when I look at this, I think I'm happy with that. The reaction, so the solution is increasing in energy or increasing in heat, which means that the reaction must be releasing that heat in order to cause the solution to rise in temperature. So we expect a negative value. So I feel good about it. Yeah, I'm going to go with E. Alrighty, so I guess I can call it there. That's the end of the exam. For the students that showed up to the review session, I do have my notes underneath this as well, so I will send that out in an email. I hope you find this helpful. If there's anything that you think I did wrong throughout here, you want a further explanation on what I did, please let me know, and I will be happy to answer those questions. You can just email me those questions you have. Couple of tips I have for taking multiple choice questions is if you have like extreme answers where you're looking like for the most of something or the least of something, anything in the middle will never be the most. It'll always be like one of the extremes, the lowest or a highest. So you can kind of eliminate your answer choices there. And if you have to guess, you have a better chance of guessing. Use your multiple choice answers to your advantage. Look what units you need to be in. I think that makes it helpful for solving the questions and making sure your units are all correct throughout them. And then sometimes, right, we're asking a full exam, things build off of each other. So sometimes one question will help you answer a different question. So make sure you read all of the questions. If you get frustrated on one and you're taking too much time, like I did with the balancing equations, just skip it, come back to it. It's better to get the ones that you know right off the bat and get all of those points, and then spend your extra time that you have looking at your questions that you had to skip the first time around. But this is multiple choice, so make sure you put an answer down for everything. If it's getting to the last 5 minutes and you're like, I have 3 questions to answer, make sure you put a question down, or make sure you put an answer down, even if it's just a guess, give it your best guess. Better to try and get points and get no points than to not put an answer down and get no points. Because maybe you'll guess correctly. I hope that you are studying well and your exam will go well. I will be there on Tuesday if you need anything. But good luck. You're going to do great.